More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at Home. Real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at Home is right for your child, visit mathnasium.com/at-home. Mathnasium at Home, changing lives through math.
Hello everyone, welcome back to Mathnasium Schoolhouse. Happy Monday. It is the beginning of the week. Curious to know who we have here with us today, so feel free to share your name, especially since you're under your parents' account, more likely than not. I'd love to know who we have here with us. And maybe also what has brought you here, because for today we have a title that doesn't necessarily tell us what we're going to be looking at today, right? And I kind of did that on purpose in a sense that for those of you that maybe have experienced this wording before, have seen it before, you might know where this is leading to. And for those of you that have not, hopefully it's been curiosity that has brought you here today, which I'm hoping by the end of today you actually do have fun and learn something new. So the nice thing about today, and the topic actually, so although the title is called If This Then That, and we'll be looking at using this phrasing in our schoolhouse lesson today, the bigger topic that we're looking at is logic. And so, although again my comments aren't working nicely for me, I'll refresh them here and there, and I'd love to see what you guys, if you've already worked with logic, what it is that you guys know about it, what you've learned, and what fascinates you about it maybe, and maybe how it applies to what you learn in school or not, and in particular with math. So maybe as you guys are doing that, I'll kind of give my background as to why I chose this topic for today. Of course, all of us being mathematicians in our own little way, we know that as mathematicians, we need to make sure that our imaginations are running wild all the time, right? Mathematicians, the best of them that have ever existed, have allowed their imaginations to run wild, to really make, the way that I like to view it is make the unthinkable possible, right? And so they need to think of these ideas and see if they can prove them in some sort of way. I mean, it's a lot more complex than that, but I like to kind of simplify it and think of mathematicians in this beautiful way. And that all starts with statements, or what we would call propositions. And these statements could be true or false, and that's what we'll be working with today. And in particular, we'll work with these statements, whichever ones I put on the screen for you, or you'll see in the document which has been shared with you. You might want to follow along on that, but I'll also have the questions shared with us on the screen in just a bit. We're going to have to reason them. We're going to have to see how they relate to one another. And so that's what logic allows us to do. And there's three different things that it allows us to do. It allows us to see formally how the truth of these various propositions influences the truth of others. Okay? So if we know that one is true, what do we know about another? It allows us to see if combinations are always, or maybe just sometimes, or maybe never true. And that's how we'll conclude our lesson today before going in depth into some of these problems tomorrow, since this is a series with 2 parts. And logic also allows us to see if combinations logically necessitate other combinations. So although that might not mean too much to you right now, that's where, if you continue to study mathematics, you'll see the critical role of logic in a lot of the problems that you explore. But what I'm hoping you've already thought of, and maybe what brings some of you here today, is the relationship between math and coding, or math and programming. And that's where logic really plays such a crucial role. So hopefully some of you that are here with us today have already played with that. Maybe that's where you've heard this phrasing, if this then that. You've looked at these, what we're going to call, I'm going to just go to my whiteboard here, conditional statements. So let me just write down here for those of you joining just a bit later. Again, I'm not able to see the comments, so I apologize in advance if you're asking questions. I'll address them in just a bit when I refresh my screen. We're looking at logic, and we're going to start just with an overview of what these conditional statements are, which is what our title of today's lesson is referring to. So let me just write that down here. Okay, well, as I said before, you can choose to download the document, the file that's been shared with you. a few hours ago on our Facebook page, which is the worksheet that I'll be using as follow along problems. And then there's also a practice page at the end for you to use for more practice at the end of today's lesson, especially in preparation for tomorrow, our second lesson on this topic. So let's begin here. And maybe I'll just make a mention as well that this isn't necessarily a topic that you get to explore in school. There's just so many other interesting things to see in the math classroom. But you might have, with some of these wonderful teachers that exist, of course, they might see the necessity of bringing logic into the math classroom, which is wonderful. But one thing that if you are interested in learning more about this, you might choose to reach out to nearest Mathnasium, and we'd be more than happy to, on top of creating a customized learning plan that fits your needs, your math goals as a student, we'll also be sure to supplement it with these enrichment topics that, and maybe I shouldn't call them necessarily enrichment topics, but these topics of interest, those topics that really get you excited about learning more and more about math. So let's begin here. I hope that you can follow along with me and help me out, as always. We're going to look at conditional statements, and we're going to start with implication. I'm not going to write that down just yet, but what I will write down is this. We're going to have to get used to some notation here, some syntax, but that is perfectly fine. Okay. You might see this written this way or with 2 lines. I might go back and forth with both, so hopefully that's not too confusing. But what does this mean here? I'm going to tell you when we're going to use that throughout the lesson. So if P is true, Q is true. And I'm going to use the wording of our lesson for today. If this, then that. If P is true, we're just going to use that variable. It's the typical variable mathematicians will use in studying logic. If P is true, then Q is true. Okay? This is this is what is referred to as implication in many ways. This is an example of a conditional statement. Okay? Just bear in mind, and we'll see this through examples, what we're not saying here is anything about P being false. We're simply saying here, if this, then that. And definitely not saying anything in regards to P causes Q or anything like that. This is just a statement. Okay? And one other way that you might want to look at this, which at Mathnasium is a lot more friendly for us, we can write this down as if some hypothesis, better seen through an example in just a bit, if some hypothesis, then some conclusion. All right, so I just want to leave this on the screen for a bit before we move on to our first problem. And maybe as I leave this on the screen, maybe I'll say one out loud, and then we'll move to our follow along worksheet in just a second. So let me say one example here would be if a number is positive. So think about that for just a second. Maybe what would you finish that statement with? And I have one which I'll give to you in just a minute. But what would you finish that statement with? If a number is positive, then what? What could we say about it? One might be, if a number is positive, then it is greater than 0. Okay? If a number is positive, then it is greater than 0. Hopefully all of you are saying, yeah, of course, that's true. If a number is positive, then it is definitely greater than 0. Okay, so that statement is in fact true. Let me go to the PDF that I have here prepared, the follow along worksheet, and present to you the first problem at the top of that page. And as I erase my board here, prepare it for question number 1, I want you to think about how you would rewrite this statement here, which I'll read aloud in just a second, as a conditional statement. So right now we just have a statement. How would we write it as a conditional statement using this hypothesis and conclusion that we just talked about, that I just presented on the whiteboard? So how can I rewrite the statement, a triangle with 3 equal sides also has 3 equal angles, as a conditional statement that follows what the structure that we have there on the worksheet? If something, if hypothesis, then conclusion. I'll give you a second to think about that, and then we'll write it down over here. Okay. Hopefully you're thinking, okay, this is not too bad so far. I can simply take, and I'm just going to highlight the if and the then. So So using that original statement that I have there in the question itself, I can say if a triangle, what does it have there? If a triangle has 3 equal sides, I'm just going to use some short forms here for the sake of time and space, then it also has 3 equal angles. Then it also has 3 equal angles. So we just rewrote as conditional statements just to get us comfortable with writing these in the if and then statements. And again, I'm going to reinforce this idea so that you can kind of see the application of using this type of logical reasoning in other areas. If you're, this is based on very limited knowledge of coding and programming from my end, but I do understand that if I'm trying to tell a program to do something for me, I need to be able to present it with commands that hold true every time I want it to hold true. Okay, so I need to get comfortable with writing these statements because the program will only listen to what I tell it to do, what I direct it, what I command it to do. Again, based on very limited knowledge of all of this, but I do understand from my math perspective that this is critical. Given all of that, let's move on. So those are conditional statements, just very, very basic, if this, then that. Great. Hopefully we're comfortable there. Next, we can start to talk about the converse. So I'm going to move away from my follow-along document for just a second, go back to my whiteboard, and present on the screen the next type that we'll look at, which, as I just said, is the converse. If any of you know what this is, go ahead and share. But this is simply, the way that you're going to look at it for me, is simply switching that hypothesis and that conclusion. And so how can I rewrite that using the variables and the symbols that I used before, that same syntax? Well, if Q, then P. I'm simply switching. I switch the hypothesis and the conclusion. So for example, going back to that example that I used in that first problem that I just stated out loud, we talked about if a number is positive, then it's greater than 0. If I take the converse of that, I can say if a number is greater than 0, then it is positive. We're not talking about the truth just yet. We're just simply changing up our statements using these rules. So if I want to take the converse of that original statement, I would say if a number is greater than 0, then it is positive, and I just have switched the conclusion and the hypothesis. All right, so then let me go to that PDF here and scroll down for all of you to show question number 2, which is where I'm going to ask you to help me write the converse of this statement, which is the same one as we had before. A triangle with 3 equal sides also has 3 equal angles. How can we write the converse of that as a conditional statement? I'll give you a few seconds to think of that. So given that original statement, how can I find the converse? Again, we're just switching it up, so nothing too complex just yet. So I can say before I write it down, if a triangle has 3 equal angles, then it also has 3 equal sides. Okay? If a triangle has 3 equal angles, I'm going to use short forms, I apologize, then it also has 3 equal sides. Now, I'm going to pause there for just a second before we move on to a few more conditional statements, types of conditional statements. I'm going to pause there and ask us to think here, is the converse always true? I'm going to pose that question to you. We looked at 2 examples. I said if, I gave you 2 examples. So this one here is just if a triangle has 3 equal angles, then it also has 3 equal sides. Okay? And the other one was if a number is greater than 0, then it's positive. So I want you guys to think possibly of an example or just about the converse itself and what you know about it. Is it always true? So I'm going to refresh my comments. Maybe this is a good time to do it. And I'm hoping to see an example. more so than maybe yes or no. If you have an example of of possibly how it's always true, or another example, or maybe an example of where it's not true. Curious to know. Let's see if the comments will be nice to me today. Some of them are great. Okay. So let's see here. Can we think of an example where the converse wouldn't be true? I'm going to pose a statement for you, and you're going to think of what the converse is, and then you'll be able to answer that. So let me maybe go to just my whiteboard here. So let's say I have the original statement be if a figure is a square, then it is a rectangle. And hopefully from here you can see, oh, okay, so the converse is not always true, because if we're just switching the hypothesis and the conclusion here, we would get, of course, maybe I won't write it out, but I'll say it out loud. Let me maybe make that nicer. Not that that tells you much, but we'll hear it in just a second. So the converse of this original conditional statement would be, if a figure is a rectangle, then it is a square. That's kind of ridiculous, right? We should be able to think, well, no, sometimes a figure is just a rectangle and it's not a square, because although it has 4 equal angles, 4 90-degree angles, it doesn't have to have 4 equal side lengths, which would mean it's not a square. So we know here that the converse is not true, and so we can confidently say that the converse is not always true, even though our first 2 examples we saw that it was true. Okay? Just something to keep in mind. We're going to move on to another type here, and we're going to look at the inverse. And just before we look at the inverse, we need to understand something about negating statements. So let me erase this here. I will write the inverse. That's what we will observe here. But before we do that, let's look at what it means to negate statements. So to negate statements, we're looking at actually the opposite. Negate, hopefully you're thinking, okay, that sounds very much like negative, and that hopefully you start to think of the opposite. Think of positive and negative numbers, kind of thinking of them as the opposite numbers of one another. -5 is opposite of +5. And so when we negate a statement, we're looking at the opposite. And there's a symbol that we use, and that looks something like this. So let me write here, this means to negate. Find that opposite, okay? So very simply put, a truth statement becomes false, and something false becomes true. Just the opposite, okay? So for examples, and I'm not going to write this down, but for example, if I was telling you that all apples are red, you would come back to me and say, well, no apples are red. Complete opposite. All apples are red, no apples are red, right? So we need to understand this when we talk about the inverse. And why is that? To take the inverse of a conditional statement, we actually negate both that hypothesis and that conclusion. So we would write it out as, and I'll take out my red here, if not P, then not Q. Maybe that's the best way for me to put it. All right. So for example, going back to that series of examples that I had with positive numbers, I could say something like, if a number is not positive, then it's not greater than 0. That's my example there. And we'll do an example together on our PDF here. Let me just scroll down to question number 3. And I'm going to ask you guys to help me out in writing the inverse of that original statement that we've been working with together. Please find the inverse of it and just, again, write it as a conditional statement. So if this, then that. And you can use what's been cut off a bit here. Maybe I'll help you out here. Just move it down so it shows up on your screen. If not P, then not Q. All right, take a few seconds to think of that. I know some of you might be thinking this is completely different from what I've seen in school, and honestly, I'm quite glad. Sometimes our schoolhouse lessons really focus on what it is that you learn in the curriculum in your area that your teachers are ready to present to you, and other times it's kind of outside of that, but it's still within the realm of mathematics. And in a cool way, how mathematics relates to so many of these other things that we love and enjoy that are part of our real world. So hopefully you're starting to see that connection. Some of you might just find this interesting and curious, and that's all that has brought you here, which is great as well. So let's look at number 3 here. We're trying to find the inverse of the same statement we've been working with in the past. A triangle with 3 equal sides also has 3 equal angles. All right, so how are we going to write that out as the inverse? What we could say here, I'm just going to, again, fill in if and then, just to keep that same structure we've been following. So if a triangle does not have 3 equal sides, right, I'm negating that. I'm not going to be able to squeeze it in. 3 equal, I'm going to place it up here. I did it. Then it also does not have 3 equal angles. Squeeze it in as 3 equal ang. There we go. All right. If not P, then not Q. If not the hypothesis, then not the conclusion. Another way to think of it. Now let's observe, before I move on to yet another conditional statement, let's observe here, and let me ask you, is the inverse, or does, sorry, let me rephrase that. Does the inverse always have the same truth value? And what I mean by that is it always true? Is it always false? As the original. So if the original is true, will the inverse also be true? If the original is false, is the inverse also false? So think about that for a second. What example could we possibly come up with where that original is true, but the inverse maybe, it's not that it's false, maybe it's just not always true. Take a second to think of that. You don't have to necessarily write it out, but maybe start to think about where that might be the case. I'll share with you my example here. I'm just going to remove this. So the inverse, let me pull out a new color here. The inverse does not always have the same truth value as that original. Okay, just a fun observation to make. And one example, one great math example, if we resort to some of our knowledge of divisibility, I can say that, let me call this the original. I can say that a number, so if a number, I'm going to use a lot of short forms here, so hopefully you're following along with what I'm saying here. If a number is divisible by 4, then it is also divisible by 2. And hopefully you're thinking, oh, of course that's true, because 2 is a factor of 4, so anything divisible by 4 will then be divisible by 2 as well. Now, what if we created the inverse? I'm not going to write it down much like I did with the converse before. Okay, so think about the inverse here. If we do that, if not P, then not Q, let's see if that's always true, not always true, or always false, something like that. The inverse here would be, well, if a number is not divisible by 4, then it is not divisible by 2. Hopefully you're all thinking, well, hold on, I can think of a few examples where that's not always true. Sometimes, but not always. Right? What about the number 10? It's not divisible by 4, but it is still divisible by 2. So we can confidently say, because we've thought of at least one example, we can confidently say that the inverse does not always have that same truth value as the original. Cool observation. All right. let's move to yet another type of conditional statement we can have. So I'll show you the follow along document in just a second. If you're looking at it, you will see that our next type is the contrapositive. So let me write that down here. Slightly longer name here. The contrapositive. Okay. Hopefully you're starting to think of the two parts of that word, and maybe you can get a sense of what it means and what role that plays with our original conditional statement. Here what we're doing, we have to use our knowledge of negating. We're going to negate the converse. Okay? So to negate a converse, hopefully you're thinking, oh, okay, then first I have to find that converse and then I can negate it, which means to negate both the hypothesis and the conclusion, to negate that entire statement. Okay? The way that we would present this would be this: if not Q, then not P. Okay. So I'm just going to jump to our follow along document here, and let's just do one together. So let me make sure we're scrolled down to question number 4. Still on page 1, question number 4, if you are following along. There are kind of two parts to this question, so we'll do that in just a second together. And then we'll make an observation about the contrapositive. All of this will help us for tomorrow's lesson. So write the contrapositive of that original statement we've been working with, which is that a triangle that does not have 3 equal sides has 3 equal angles. So slightly different. So how do we find the contrapositive of that? So if something, then something else. If this, then that. I'm going to prep us here. Go ahead and take a few seconds to think about that. Again, I really do apologize for not being able to see the comments today. It's still a bit faulty for us. So we'll try to get that resolved. But hopefully, if you're not commenting, then at the very least, you're thinking about these and kind of checking your answers as we go along. So if this, then that, we're looking for the contrapositive of that statement there. I'm going to start to write it down here. If a triangle, just make sure it's all on the screen there. If a triangle does not have 3 equal angles, I'll use short forms again, kind of, then it has 3 equal sides. Again, we're not talking about the truth value just yet of this statement. We're simply writing the contrapositive of it. So let's not start to get too in depth into, wait a second, this doesn't hold true all the time. Right, so we've found the contrapositive. If not Q, then not P. All right, so we can see that there. And now the question is, the second part to this question is, since the original statement is false, so going back to that, the original statement was a triangle that doesn't have 3 equal sides has 3 equal angles. We know that that's false. So since that original statement is false, what could we reasonably say about the contrapositive? Without even knowing that relationship, which we'll conclude in just a second, we can look at the contrapositive that we formed on the whiteboard here. We can say, hold on, if there's anything I know about my shapes, it's definitely about triangles, and it's definitely about equilateral triangles, and I know that this is false. And so since we can say that since the original statement is false, then the contrapositive is also false. And so we can conclude, and I'll confirm for you, that the contrapositive is actually always has, I should say, the same truth value as the original. So if the original was true, the contrapositive would be true. And as we just saw, if the original is false, the contrapositive is also false. And although we won't maybe explore this on the whiteboard, the same is also true for the inverse and the converse. So maybe I'll allow you to explore that on your own, all right? So that we can move on to question number 5 here, before we look at the next question on page 2. Here we're just being asked, we'll talk about if and only if statements in just a second. We're being asked to rewrite a version of that original statement we've been working with that says if a figure is a triangle, then it has 3 sides, and if a figure has 3 sides, then it is a triangle. We want to write this as an if and only if statement. So another cool fact about conditional statements, and I'll prepare my board here before we go back to that follow along document, is that if the original and the converse are true, so if original and converse are true, what could we say? We have what we just saw in the question, this if and only if, which can be represented as this. We don't always have to write out all those words. We can say if with two F's, and that means if and only if. And what that means for us, if we use the same syntax we've been working with today, if this and the other way around. If P implies Q and Q implies P, we can write it as simply this, or using this syntax here, this wording, whatever we want to call it. Let me add some wording in here so it can read nicely. We can say it like this. All right? So again, let me repeat that. If the original statement and the converse, we'd have to find the converse, and if we confirm that both of them are true, we have an if and only if statement. Just another cool fact that we can use. And so what that means is if P implies Q and with the converse, Q implies P, then we can rewrite it as this or this. And what that means for us is that we have an if and only if statement. Pretty cool. We're going to go to question number 5 here and use what we just learned to write our if and only if statement for this. So how can we write that statement that I read earlier into an if and only if statement? Well, I could say that a figure is a triangle if and only if. And so I'll just use that if with the double F. It has 3 sides. And how did I know that statement was my if and only if statement? Well, going back to that original, it told me if a figure is a triangle, then it has 3 sides. So that says if P then Q. And then that second part of that statement was just if Q then P. If the figure has 3 sides, then it is a triangle. So I can rewrite it as this. I'm aware of the time, so let's do one question from the next page, which just reviews everything that we've talked about. So nothing new left, just taking an original statement, writing its converse, its inverse, and its contrapositive. Who else thinks of the shoes when I say converse? Every time I say it, I'm thinking of that. So it's probably one of my favorites. But let's see here. So we're going to look at question number 6 only for the remainder of the time. And its original statement is if a figure is a square, then it is a rectangle. So we've seen one similar to this. So maybe what we could actually do is skip that one. You know what? I'm going to make a decision right on the spot. Let's look at something different, maybe not so mathy for a second, although it kind of is if you think of probability. If it rains today, then I do not go for a walk. Let's stick with that. Let's see what we can do with that information to write the converse, the inverse, and the contrapositive. So we're looking at question number 7 here, which I might not even write. Let me write each one that we're looking at. So let's start with that first one, the converse. What could we say here? So if the original is if P then Q, the converse will be if Q then P. So I'm going to take out my green maybe, and I'll say the converse here is if I do not go for a walk, then what? Then it rains today. Sorry. Looking at so many sheets here. All right. Again, we're looking at the converse. So if the original statement is if P then Q, the converse will be if Q then P. So I've switched those two. Again, that's just a review of what we talked about today. Let's move on to that second part. Let's look at the inverse. So all I have to do here, switch that beginning up, and look at the inverse. So this is where we start to talk about negating parts of a statement. And so in the inverse, that's exactly what we have to do here. we're going to negate both the hypothesis and the conclusion. Okay, so negate both P and Q. And so how do we write this? Well, if it does not rain today, let's squeeze in today, okay, then, we're writing always as a conditional statement, then I go for a walk, or I will go for a walk. I go for a walk. So again, I've negated P and Q, the hypothesis and the conclusion. Originally, we had if it rains today, so then the opposite of that is if it does not rain today. The original was I do not go for a walk, and so you're going to say I go for a walk. And let's look at that last bit before we end for today. We're going to look at the contrapositive. So I'm going to write that out, maybe while you guys think of what this would look like. Okay. Remember when we talked about the contrapositive just a few minutes ago, we talked about negating the converse. So we found the converse in the first part of this question. So now we're just going to have to take the opposite of that, negate it. So for number 7, contrapositive, we're going to have here, if I go for a walk, appearing, if I go for a walk, then it does not rain today. All right. Okay, so again, the contrapositive tells us if not Q, then not P. Q is our conclusion. So originally we had said, I do not go for a walk. This time it's if I go for a walk, I will go for a walk. And then we have to say not P. So originally it was, it rains today. So we take not P, which is it does not rain. And that's our contrapositive there. All along our lesson today, we made some observations, so keep those in mind for tomorrow. Tomorrow's session will begin with a review of what we did today, but I'm going to stick with the syntax, so maybe if you find it a good use of your time in preparation for tomorrow, you'll want to review today's lesson. Maybe make yourself a little cheat sheet, or reminder sheet of these different notations that we use here, and we'll use them tomorrow when we look in depth into some of these statements and relate them to one another more so than we did today, and build some truth tables, which is the next step once we're comfortable with these conditional statements. I apologize once again for not being able to see the comments today. It's one of my favorite parts, is seeing you guys contributing to the conversation, the discussion in our Schoolhouse lessons. So I'm really hoping I get to see that tomorrow. More of an opportunity for you guys to participate. I hope you guys found this interesting, something different. There are countless logic puzzles out there that get students to really think outside the box and put a lot of their math minds together to solve puzzles that use this logic. So go ahead and explore those if you have the opportunity to do so, or reach out to nearest Mathnasium for more of them. And I know that our instructors who love math would be more than happy to do those with you, for sure. I highly guarantee it. I hope you guys have a wonderful rest of your day. I will see you tomorrow. I hope you all join. Thank you. Be safe. Bye-bye.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.